So, I was a bit confused yesterday when I saw at the end of the lecture that we were already at the matter theory, because I had planned to have 5 lectures, and that would mean it would be the last one today. But indeed, I did not talk about the semantics yet. I'll do that quickly now. Before we start, we remember there is this set of abnormalities which we call omega. It is defined by a logical form or a set of logical forms. And then there are, for any gamma, there are some delta such that this is a classical disjunction of abnormalities, what is meant here. So all members of delta are abnormalities, and this is actually like the disjunction, classical one, of all the members of delta. So we have seen that yesterday. I think it was sufficiently clear in some examples that sometimes if abnormalities would be derived by lower limit logic from the premise set, things would be very simple. But unfortunately, they are not. So you have disjunctions of abnormalities that are decidable, and then you have to decide how shall we handle the disjuncts. And that reveals the idea of the strategy. So U gamma are the abnormalities that are unreliable on gamma, on the premise set gamma. So that means whenever the Costa disjunction of delta, delta being a set of abnormalities, is derivable, it's of course a finite set because this should be a formula. So whenever that is the case, then all members of delta, so we could delta 1, delta 2, that these are all subsets of, so all members of a delta for which this holds, all those members are also members of the set of unreliable formulas on gamma. You do something different for minimum abnormality. This is for reliability. For minimum abnormality, you define what accidentally was called phi gamma. And there the idea is you take from every such delta, suppose you have the deltas are delta 1, delta n, and can be infinite even. So you pick from each of these deltas one member, that gives you a choice set of the deltas, and then you pick the minimal choice sets, those that are not proper supersets of other choice sets. And this, that is phi delta, those choice sets. Is it clear for everybody? Because I wasn't interrupted yet, which is strange. The previous days I would have had at least 3 questions already. Which means the audience is 1 awake, 2 is following what I'm talking about, and 3 is minimally interested to form any questions in your brains. And I have not seen a proof of that until now. Okay, so please be more clear.
Assume it by default.
Sorry. I go to the place where I can, where it gets interesting for us, I think. Now if you have in mind what U gamma and phi of gamma are, it will be simple to define the semantics, because you start from the, in my case, the Clun models of gamma. Of course, you can also start from the LP models or from another, take another paraconsistent logic. So this is the lower limit logic. But it has not to be Clun, that was just for my examples. And then you say this, from these Clun models, you pick those that are the reliable Clun models. What is meant by that? Well, if you have a model M, then let M abbreviate the set of abnormalities verified by this model. So this is just the A that are a member of omega that are verified by the model. Okay? And then you say that a Clun model is reliable if and only if the set of abnormalities of M is a subset of U gamma. In other words, M does not verify any other abnormalities except for those that are unreliable given the premises anyway. Okay, so that's a very simple idea. And the other definition for minimal abnormality, I take the simplest one because there are several ways to define this. This is minimally abnormal. Minimally abnormal model of, maybe I should always add that, of gamma. Because there are people that think that there are minimal abnormal models and not minimal abnormal models in general, but that's nonsense. It's a model can be minimal abnormal model of gamma. It has to verify all members of gamma, and then among the models that do that, be minimal abnormal. Okay, it's not minimal abnormal in general. There's no absolute, it's a relative notion, not an absolute one. So what does that mean? That means that the set of abnormalities, well, there is a lowercase phi that is a member of phi gamma, such that the abnormalities of the model M are phi. In other words, or a different way of writing it is to say that M is minimally abnormal model of gamma if and only if M, the set of abnormalities verified by M, is a member of phi gamma. This is interesting because, well, the completeness proof simply consists in showing at the syntactic level, which is quite simple, that there are the best way to get there pedagogically at this moment. Just recall the definition for a minute. So if you have U gamma and phi gamma, then this is very simple. And this really means you can show that it comes to, if you think at these deltas, of course, every model of gamma has to verify each delta, because the disjunction of the deltas is a lower limit consequence of gamma. So every model of gamma has to verify all the top deltas. So it has to verify, since this is a classical disjunction, it has to verify at least one member of it. of every tap delta. So that means the same as picking a choice set. Okay? And you take the minimal ones because you say, I'm going for minimal abnormality, not just those that verify no other things than that set of things that are in phi gamma, but also among those you minimize. So let's see for a second, as this is rather essential, as the whole semantics where it is clear. The interesting point, of course, from the meta-theoretic point of view, in order to produce the proof, the interesting point is that you can show that the minimal abnormal models are exactly those such that the abnormality is verified by M is a member of phi gamma. It is a minimal choice set of all the disjunctions of abnormalities that are lower limit consequences of gamma. There are some other strategies, most of them not very interesting. Like there is a strategy I like to call blindness. Namely, if you derive an inconsistency, you don't see that it is an inconsistency. That seems to be a form of blindness, right? So if you apply that, then you get classical logic. I would not dare to say this in Poland, because they might put me in jail. I've never been in jail in Poland, but I have several times been excommunicated. For example, by Richard Wojcicki. Okay. So I just continue through the slides to check whether there is anything that might be. So if you have that in mind, also the marking will be very transparent. The definitions are here. I shall put the slides on my homepage. My homepage was in the beginning of the thing, but you can find it by just Googling my name, and then if you add CV, preferably dash lowercase e, the English version of the CV, then you will find there all the information. My password is not on it, but my home address is, not my phone number and things like that. So this is the hint for the proof, the thing in brown. Things in brown are normally meant to clarify something, but are not essential to understand the way in which the slides follow. But they are kind of like footnotes, you could say. So the fact that you can show this is very important because that's the clue for the completeness proof. Then here the marking is illustrated, but we went through that yesterday. There is something missing in the, we had also problems yesterday. There is something missing here in that the mark should disappear, of course, when we go to the marking for minimal abnormality. This was the marking for, above the green line was the marking for reliability. That's again in terms of this discussion like for game theoretic description. And now we get to the meta theory. We don't have to rush through all of that because there still is some time tomorrow. Okay. So you can define A as a reliable consequence. There is a superscript R above the adaptive logic AL. So the R refers to reliability. A is a reliable consequence of gamma if and only if for a finite delta in gamma, A or the classical disjunction of the members of delta is, I prefer to show it here, A or classical disjunction, the classical disjunction of the members of delta is a lower limit consequence of gamma, and the delta are all members of these unreliable with respect to gamma. Okay. The fact that delta need to be finite is just to make sure that this formula is a formula. Okay, if delta would be infinite, classical disjunction of an infinite set of the members of an infinite set is not a well-formed formula. If you have only a finite well-formed formulas.
Excuse me.
Yes?
I didn't quite get it. The delta intersection, the U gamma is empty. Okay, it's what's written. But you said it has members in the U of gamma.
Sorry, could you repeat the question?
It's because you said that there was a.
You say something about that, yeah, this was related. If I said that it was related to the marking. So when you have a proof, you can just go to an example on the slides quickly, then I don't have to write on the blackboard. Like here in why are lines 6 and 7 marked? Because on the conditions is respectively singleton P and not P and singleton Q and not Q. Whereas on line 8, you see that typically such a disjunction of abnormalities, so that's such a delta. Delta is the set containing P and not P and Q and not Q. And what you see there at line 8, what is derived is the classical disjunction, because in Clun, the disjunction is classical, just as in LP, for example. So the fact that the condition of line 6 overlaps with a delta that has this property, classical disjunction of the members of delta is LLL derivable from gamma. So that means that the line is marked. Whereas line, suppose you have R and not R, you could derive something on the condition R and not R. That would not be marked because R and not R does not belong to any such delta. But this is different from everything else, from other things I said. It's a local definition of when some line should be marked. Now, can you continue is there still a point in continuing the question for you?
Yeah, it was just written that the delta intersection, the U of gamma was the empty set. So I thought that.
No. That there, the delta that was in a construction, in an example, sorry, where you had a line, so saying line I, and that gave there was a formula here, and then there was a justification, so referring to some previous lines and the rule, and then you have here as condition a delta. So of course that delta is. Now delta is used to refer to such a thing there, whereas what is used here is an example of, like here, the formula of line 8. Okay, so just still a finite set of abnormalities, but
No, no, yeah.
Yeah.
Thanks.
thank you. Okay, more questions at the moment? No? Okay. Of course, I do not produce the proofs here. The proofs have been published in the first volume of Universal Logic Journal, Jean-Yves Journal. Jean-Yves is not here at the moment. Okay. We shall put it in a corner when he comes in. Good. Now in Graham's first paper on LPM. So LPM is not an adaptive logic in my sense. It is not in standard format. There are a number of huge differences. The criterion are straightforwardly semantic, but they are not semantic in the same way as I do it here. For example, the abnormalities that models verify, in my sense, then I just mean a formula that is an abnormality like A and not A, and at the same time is verified by the model. But for Graham, an abnormality refers to a different notion in the syntax. It is related to, in the semantics, sorry, it is related to a different approach to the semantics in general, not to which formulas are verified. But for example, if you have the extension of a predicate, there can be inconsistencies at the level of the model, in a sense that some object of the domain both has a property, it's in the set of things that have the properties, but also in the complement of that. Okay? So that has nothing to do with verifying, because if you have 7 objects, but they have no name, like think about non-standard models of arithmetic where you have the non-standard blocks, the numbers in the non-standard blocks will not have a name normally. So then that just gives you, there is an X such that. So even if there is an infinite one of them, it's only one formula that is verified by the model, in my view, whereas for Graham will count an infinite number of abnormalities in that model. Okay, so in this sense, the approach is totally different. Also, my approach is older, but that's not, I think I'm older than Graham, a year or two. I'm not, I don't remember exactly.
Yeah, you're on that.
I'm from 44, yes. But that doesn't make me either more stupid or whatever, okay? Of course, Graham hopes that I will die first, but that doesn't follow either.
Well, that means you get to heaven first, Dick.
Okay. I think that was all I had to say on the thing. And so remember, I think I made that clear yesterday. In general, you have first your lower limit logic that has some consequences, then you have the reliable adaptive logic gives you some more consequences, and then if you move to minimal abnormality, you get still more consequences. And of course, then you can move to classical logic, you get immediately everything. So that's still more consequences. Okay.
Hey, can I just ask a question? You're doing the propositional case here, right?
No, the definitions are general.
So you're doing first order logic.
Sorry?
You're doing first order logic.
Yeah. The examples are all propositional,
Okay.
but
But the definitions.
the definitions are first order.
Okay.
Yes. Okay. So then I think we can go to the meta theory. So this first characterization of when A is syntactically irreliable consequence of gamma is useful because it is really that theorem that shows that you have completeness and soundness. That the criterion for this criterion for at the syntactic level immediately translate to the criterion we used for semantic consequence. It's obviously the same thing, it's structurally the same thing. Given that you have your lower limit logic, to learn or whatever, your lower limit logic is supposed to be sound and complete with respect to its own semantics, okay? To start from there, otherwise there's no point in doing the whole exercise. So this is just the theorem and the lemma that you need to prove then to prove soundness and completeness, first for reliability, next for minimal abnormality. Okay. Then strong reassurance. The notion of reassurance was originally introduced in Graaf's Studia Lógica paper on RPM, and the reason why he wanted it was that he said, well, if you by taking LPM instead of LP, so by minimizing abnormalities, use if a premise set has LP models, then it will still have LPM models. If it has no LPM models, then according to traditional views at least, triviality follows. Okay? Which is something that one could attack, but you didn't. You just said if it has, well, what I call lower limit models, then it has also adaptive models. That's how I would translate to my system. I would translate reassurance. This is very important because, and it was brought up in the literature on non-monotonic logics already in a very old paper by Magidor and some other people, computer scientists, that pointed to the difficulty that you have when you have infinitely descending sequences of less and less abnormal models. Okay? So suppose you say, think about arithmetic, think about all the natural numbers, and even if you continue in the non-standard blocks, you say, well, and to take two axioms. The first axiom says sum of these numbers is inconsistent. And the second axiom says if a number is inconsistent, so is its successor. So that means from a certain point on, all numbers are inconsistent. For example, in the sense that they are both identical to themselves and different from themselves. So clearly, here is your line. If this number is inconsistent and you want to get a less inconsistent model, just declare the next model inconsistent. So the next number inconsistent. So here you have 17 and this is 18. And so if 17 is inconsistent, then you have every number from 17 on inconsistent. And then you have a less abnormal model if you take it starting from 18. But of course you can't go on ad infinitum. You can always find just by moving the first inconsistent number one step further. So you can go on ad infinitum. And there's no minimum. There is no minimum abnormal model if you look at it like that. Okay? So that's not an objection to my approach in the sense that the numbers, suppose that these are the non-standard blocks. The entities in there have no name anyway. So all it gives you is if if the first inconsistent number is here, all you can derive is there is an x such that x is different from itself and identical to itself. Okay? So as soon as your least inconsistent number gets into an non-standard block, you do not get a less abnormal model by moving a step further. Because you do not have a new formula that gets either consistent or eliminated from, and so on. And of course, the problem arises for Graham's approach because he will consider all those things as abnormalities. But then you change the definition of reliability in one of your papers by saying if there is no minimal abnormal model, then all what I call lower limit models are they are all minimal, define them as all minimal abnormal in the sense that you take all those consequences. But of course then the problem with it is, at least as I see it, that you lose the adaptive bite. You do not get anything more by going adaptive then. You just fall back to the lower limit consequences.
In the case where it's not smooth, stubborn, that's true.
In the case where
Not
it is.
every case.
Sorry?
Not every case, just in the case where you've got unstoppables.
Yeah, of course. I mean, you still have, depends on the premise set. But if the premise set is like I described it here, then, yeah. So, the notion of strong reassurance is something that I made up from Graham's idea on reassurance. And the idea of strong reassurance is that if there is a model that is not minimal, then there is a minimal model that of which the abnormalities are a proper subset of the abnormalities of the first model. So if model M1 is not minimal, then there is a minimal abnormal model M2 of the premises such that all so if M1 is not a minimal abnormal model, then there always is a model M2 such that the abnormalities of M2 are a proper subset of the abnormalities of M1. So M1 has more abnormalities than some minimal abnormal model. Okay? So I think that is a rather strong property, and it is easily provable for all adaptive logics in standard format, whether they concern inconsistency with ever lower limit logic or something else like abduction or generalization, no problem. Good. And then there are a number of theorems you can prove. I just put them in a list here. Those with a red ball are the ones I better comment on a little bit. So the first thing we have seen already, the minimal abnormal models are all reliable models, but not vice versa. And then from that's connected to what I said about you get more consequences if you go minimal abnormal instead of going reliable. So these are variants of things I said already and of what I just said about M1 and M2 there. So you also have a fixed point property in the sense that if you apply your adaptive logic to an adaptive consequence set, for example, you take the minimal abnormal consequences of a premise set gamma, and then you consider this consequence set and you apply again your adaptive logic on it, you get nothing new anymore. That shows that the thing gives you a fixed point. Okay? As you like it, because otherwise you could go on ad infinitum showing repeating the same logic and so on. So you have it there for minimal abnormality, but also for reliability. Then a property called immunity is like taking the fixed point property as well as its converse. And then there are these famous properties that Mackinson was so proud about. He introduced them, cautious cut and cautious monotonicity. So although adaptive logics do not in general, and also non-monotonic logics do not in general have the cut property, transitivity, and do not have monotonicity, they have what he calls cautious cut and cautious monotonicity. So the notions are very simple, and if you're just looking at the formula, you will get them. So if gamma prime are a set of adaptive consequences of gamma, whether for reliability or minimal abnormality. If I don't write a superscript, it means it works for both. So if gamma prime are adaptive consequences of gamma, then whatever follows from gamma prime also follows from gamma. Whatever adaptively follows from gamma prime also follows from gamma. So it's not, you do not take a subset of the premise set, but you take a subset. You have to take a subset of the consequence. Okay. And then for cautious monotonicity, if you have a set of adaptive consequences of gamma, and you add this gamma prime, this set of consequences, you add them to gamma, then you get nothing new from that. So that's cautious cut. Cautious monotonicity, I'm sorry. I sometimes make mistakes in talking, so don't be afraid to correct me when I make mistakes. Because this word was really obvious. Okay.
For 7 and 8, they're called cautious because they're defined in the set of consequences instead of the premises. Is that it?
Mackinson introduced the number, I don't know why I called it cautious.
Okay.
It was clearly something weaker than transitivity and monotonicity. And so I think we have to find a name for it. I don't think cautious means much. Well, you see more or less where it comes from. If you, normally for monotonicity, you say if to gamma you add any set of formulas, okay? And here you say if you do not add just any set of formulas, but a set of formulas that are consequences, adaptive consequences of. Actually, such properties, some of these properties were proven in a rather late stadium. I wouldn't remember. I'm very bad in dates. That's why I never know how old I am. But at some point, Christian Strasser moved from Ghent. He took a PhD with us, and then he moved to Bochum. And before that, these things were proven by, and in a paper published by Christian and Peter Verdey from Université Catholique de Louvain, now in Belgium, and then me. So the idea was to, for example, to figure out when two premise sets were adaptively identical or equivalent. For tasky logic, you can easily define two gamma and you can say gamma and delta are equivalent premise sets when they have the same consequences. And then you can easily figure out what it means that they have the same consequences and whether this is so. But you can also do it in terms of adaptive logics and make a distinction between premise sets that are equivalent for some adaptive logics and others that aren't. And we found it interesting given that it turned out, notwithstanding the fact that the aim of adaptive logics was not anything like formulating theories, it turned out that it is interesting to formulate adaptive theories, or at least it looks interesting for people doing adaptive logics like me. For example, I wrote a paper on, and Peter Verdey wrote several papers, but let's say that there were some problems in them still. And, but we wrote papers on adaptive approaches to Frege's set theory. So where you take Frege's axioms basically, and then define an adaptive theory from them instead of just a deductive theory, defined in terms of a tasky logic. That was the paper published several years ago in Studia Lógica, and you can easily find it on my homepage. And I think Studia Lógica, of course, does not defree the paper because it's in the hand of Springer. I found out that for a paper I published in 92 or 93, I don't remember exactly, they are still asking a lot of money if you want an electronic copy of it. Now, the proof in the paper was the first time that this proof was published. In that sense, it was worth to have a paper. It appeared in Studia Lógica. But today, the proof is dated in the sense that there are much more elegant proofs and more general proofs. And then I started looking at papers of friends that were older than me, or are older than me, like Ilkka Niiniluoto, for example, from Helsinki. And I found a paper by Ilkka from the 80s, and Springer is still asking money if you want an electronic copy. So I think this is a shame. Yeah, well, there are so many things that should be in the hands of academics or whatever, but are in the hands of businessmen that have their only interest is maximizing profit. So, is Eduardo in the neighborhood? Yeah. So this is one of the reasons why I sympathize with certain theses of Karl Marx. And you don't, okay? I refer to that. Now, an interesting thing is to consider what I call normal premise sets. So normal premise sets is premise sets that have models that verify no abnormalities. Okay? And as we have seen, as you may expect from 2 days ago, if you have a normal premise set, for example, with respect to inconsistency, then you will get the upper limit consequences, namely the classical consequences in this case. So this is something that, as João pointed out to me at some point, is not so important. In some papers, I kind of made a lot I made some pump and circumstance about it, and Joao said, "Why do you do that? Is it so interesting?" No, it's not. So he was right. So what you see there is that if gamma is normal, then the upper limit models of gamma are identical to the minimal abnormal models of gamma and to the reliable models of gamma. And as a result of that, the reliable consequences are identical to the minimal abnormal consequences are identical to the upper limit consequences. And so this Graham has used this a couple of times to make philosophical claims, namely, people often say, yeah, if you look at the history of mathematics, it's full of applications of classical logic. Yeah, but why should it be classical logic? Maybe it's an adaptive logic. And as the thing is consistent, if it is, supposing it's consistent, then of course you get all the adaptive consequences, but that coincides with the classical consequences. Okay? So you cannot figure out whether the logic that was used to formulate or to prove the properties, whether this logic is classical logic or an adaptive logic, you cannot figure that out. It's a kind of claim you make about something that you cannot see. It's like in quantum mechanics, hidden variables. Good. Now, of course, the reason why Graham presses this is that he does not like that there are very sensible applications of classical logic. I think that's the basic reason why he prefers to consider it as rather, well, then something special should be the case if classical logic is underlying it. I was at 2, I think. So if gamma is abnormal, then you see what you get. You do not have the previous thing, but you have some subset properties. And then the like 4 is just referring that to satisfiability. So that's just phrasing it in another terminology, but there's nothing new there. And 5 tells you exactly when the lower limit consequences are, when you have an adaptive gain. So you have the lower limit consequence. In which cases do you have more adaptive consequences than lower limit consequences? Well, it relates to what happens in terms of models. Then it's a bit more complicated for minimal abnormality. But it's interesting that you can characterize it. That is not just, well, we don't know. You can say exactly in which cases an adaptive logic based on minimal abnormality will give you more than your lower limit logic. And you see the condition described there. And then in the end, I come to reassurance, namely, but it's a rather, in this case, or for these systems, for the adaptive logic in standard format, it's a rather simplistic consequences of strong reassurance, namely that if you have lower limit, well, if the set of minimal adaptive consequences and the set of reliable adaptive consequences, these sets are non-trivial if and only if Must be a mistake, I'm sorry. There must be a reference to the lower limit logic. Yeah, the last subscript L should be superscript M. Here should be, this should not be the minimal abnormal consequences, but the lower limit consequences. Because this is sufficient to, well, there's an equivalence, of course, but that's the important thing, that the adaptive logic with respect to non-triviality, well, the adaptive logic never leads to triviality if the lower limit logic does not. That was the original statement of the theorem, and that follows here from strong reassurance. Are you the watch, the keeper of time?
Have 3 more minutes, but I was not checking. But you started 10 minutes, like 15 minutes later, so you can.
I wanted to leave some time for questions, but it's too early for questions. I know what time it is.
There's a question over there.
I have just a clarificatory question.
Yes,
But,
please.
can you give an example where we can identify where the low limit logic is better than adaptive logics?
It's impossible.
It's impossible. Why?
No, that's just what I proved. I mean, how can there is an, but you'll find over there when there is an, when you get something more by going adaptive. So when you go adaptive, you always have at least all the lower limit consequences, because they are not conditional on anything. Think about the adaptive, think about the dynamic proofs. The lower limit consequences occur on lines that have 0 as their condition. So they can never be marked. That's a simple, very simple way of putting it. But it's a good question, because I should have mentioned it somewhere. I should have mentioned the answer somewhere, not the question, but the answer, I'm sorry. It's like 3:06.
Yeah.
When should I stop? The whole thing?
3.5.
3.5.
You can.
Maybe I
10
mentioned.
minutes, you can be late 10 minutes, no
Yeah.
problem.
No, but I don't like to be late. But then I mention a bit more. I just go to the next slide, and then we can have the question session. Okay. So the first theorem is called cumulative indifference. This cumulative is something like cautious. Okay. Except it means a little bit more. If gamma prime, if all members of gamma prime are adaptive consequences of gamma, the reliability or minimum abnormality doesn't matter, then the consequences of the union of gamma and gamma prime coincide with the consequences of gamma. So in other words, that's just like in classical logic, adding consequences to your premise set does not give you more consequences. That's something you have for Tarski logic, right? If from gamma you can derive A, then the consequences of gamma, maybe I have to do it here, union A are just the consequences of gamma. So by adding consequences of gamma to the premise set, you get nothing new. This is normal. This is really, I think, what should be called transitivity. Because this means that reasoning, you reason from your premises and from everything you derive from them. That's what happens there. Okay? Yeah, the next thing is that when in the beginning I was working on this paper that Graham published, and that first paper on inconsistency adaptive logics, I was tinkering, of course, saying, well, remember my task was to find what happens if an inconsistency is the people from the University of Brussels group. They wanted me to work on what happens if an inconsistency occurs in a derivation, what changes does it make? Okay, so that was the idea of understanding creativity and dynamics of the sciences in terms of Hegelian, some form of dialectics. So I was tinkering, and then very easily came to cases where either it became circular or else I got funny things like when I came there 2 days ago or 3 days ago, I said the essential thing is to separate your conditions for marking should not be phrased in terms of the adaptive logics, because then you get circularity, but should be phrased in terms of a different logic. And in my case, this is what I call the lower limit logic. Okay? And so that's what so if you have an adaptive proof, at some point I go to cases where premise set from some premise set gamma, you start by writing down premises, and then you are able to derive P, for example. And then you have another proof, and there you derive Q. What you want then, if you consider this a decent logic, is that P should also be derivable in this proof, and Q should also be derivable in that proof. Okay? Otherwise, there is an arbitrary factor that you don't want. And that is precisely what is shown here. So that were the failures I stumbled on in the beginning, and then by defining the matter differently, you get rid of it. But it's good in the end to come back to it and then to prove that you do not have that bad property. Please, yes.
I remember that this was proof confluence, but maybe you have a different term for it. Proof confluence. Proof confluence.
The proof confluence.
Not proof invariance, but proof confluence.
No. I don't think I ever used the term influence. But proof invariance refers to the fact that whatever is provable in one proof is also provable in any other proof by the same logic from the same premise. Just trying to explain you what, well, these are things that you do not always see when you begin with an enterprise, but that come up later. And then, of course, you have to deal with them. And the last thing is then these equivalent premise sets. Gamma prime is a set of adaptive consequences of gamma, and gamma is a set of the adaptive consequences of gamma prime. Then the adaptive consequences of gamma and of gamma prime are identical. So that means you can take gamma and gamma prime to be equivalent premise sets in the sense that gamma combined with adaptive logic gives you a theory, and gamma prime combined with the same adaptive logic gives you exactly the same theory. Namely, gives you exactly the same set of theorems, non-logical theorems.
Dick, I think you want a subset rather than the membership side of the last thing.
Sorry?
I think you want, we've got the membership side, I think you mean a subset.
Yes. The last theorem, we want subset signs. Gamma prime is a subset.
That's just a typo.
Let me, so it concerns this theorem?
The last one.
Here.
Yeah.
Yeah. And where is there a,
Subset rather than membership.
yeah. Instead of a membership sign, yeah, sorry. Yeah. So this should be a subset of, and this also, not as a member. Thank you. Try to remember it and change it. I'll not do it now. So maybe then, think, so as to leave the rest for tomorrow and to move to the. It's
You still
quite
have 15
fast.
minutes if you want.
Huh?
You still have 15 minutes if you want.
Yeah, but if we want to have some questions,
Okay.
then
I have a quick question.
please, yes, thank you.
Do you know any connection with adaptive logic with formal argumentation? Because I heard you name before structure and it was in formal argumentation. And do you know any connection with the field of formal argumentation?
With the theory of,
Formal argumentation. Because they both seems to be a general framework for the feasible reasonings. And
I never looked into that. Sorry, I never looked into formal argumentation. Maybe Christian Strasser has several papers on relations between adaptive logics and argumentation. I shall try to contact him and see whether we can have a brainstorm about it. It's interesting because, of course, I hope with the adaptive logics that it is a general framework to capture all forms of defeasible reasoning, but of course it's hard to prove. I think it's something that is typically shown historically. At some point it will turn out that somebody else, another approach can deal with a number of applications that I can't, or vice versa. And so, in that sense, it is good to look what the situation is today. So I contact Christian and make a note of it. Sorry. Sign in here. In here. Well, this is something we got for free. It says Jetstream, but it doesn't write.
I have a quick question. About the cumulative difference problem.
Yeah.
It appears to me much to our with flexibility relationship. What's the difference about reflexivity? Que consequent operator is reflexive. What's the difference about
A consequence set is reflexive simply if all the premises are consequences. So gamma is a subset of the consequence set. Which is not obvious. I mean, you can easily define logics that do not have the reflexivity problem.
okay.
I don't say that those logics have many applications, but you can easily find them.
May I add something I help? It is mixing with something else. Cautious transitivity appeared before, and it's the subset instead of equality on the right. The direction from left to right would be reflexivity, but it's not because he has a premise, which is gamma prime is a subset of the consequences of gamma. So it's reflexivity with a premise.
Bigger. No, right.
But it's only one direction.
No,
The other one is cautious transitivity.
okay,
Thank
thanks.
you, Joao. Okay, more questions because I'm making a note on something else.
Question here.
Yeah, please.
You're using Plan as the lower limit logic, and could you use an even weaker logic as a lower limit logic instead?
What would be the use of that? Why would I like to do that?
Yeah, because maybe you want to have to have less contradictions or anything.
No, but this thing will take care of localizing the contradictions. So lowering the set of contradictions or making the set of contradictions smaller by introducing a logic, I think might be a dangerous and somewhat arbitrary decision. Because you might. The problem is that you should always have a systematic approach if you want to have it. Because you can easily, suppose you have like in that case, no, in the case of the example I came back to at some point, we wanted to look at an example and then there was this thing. So you could say, well, let us eliminate P and not P. Let us decide that P and not P is false. Yeah, that's an arbitrary decision. Why not do it the same for Q and not Q? You cannot do both because then you have to, you will change your premise set because the premise set entails 8 by the lower limit logic, this disjunction. So you cannot throw away both abnormalities. But you could say, well, I prefer to throw away the alphabetically lower one, which is P in this case. But that's purely.
I think that would be a stronger lower limit logic in that sense.
Yeah, but this also would be completely arbitrary. And I'm afraid that if you see any way to move to a weaker logic without becoming arbitrary, I think that might be rather interesting. And that's if you find a way, send me an email. Then I buy you a beer, we meet next time.
Yeah, I don't drink beer.
Okay, anything else? Anything drinkable else? Hot chocolate would do. There are, of course, more results, but it's like many years ago I got an email by somebody from the United States that suggested to rephrase adaptive logics in terms of kind of rules you want to have the effects of And I thought there was no way to proceed in such a way to do that. So you would have a rule that, I don't know whether I still can find an example. But then the point is that at some moment I found an approach to that thing, and it is published meanwhile. But I don't find it important enough to mention it in class where I try to give an overview of the thing.
Did you buy the hot chocolate for the person? Did you buy the hot chocolate for the person who asked you the question?
Well, I didn't promise him anything. No, it just came with an alternative form of approaching adaptive logics, and the idea was so the idea basically is, if you phrase it with respect to abnormalities, say you have a rule that says if a formula of an abnormality, from a formula, the classical disjunction and abnormality, you can derive the formula. That's what you want to end up with. And then you can start constructing your adaptive logics from that point on, with that in mind. And it is possible. And it's even published. So if it's published, it's possible, right? It's published in Moscow, I must admit. And well, in a Fastschrift of a guy that certainly would have opposed the war in Ukraine.